we're going to discuss the magnetization of matter, which is the magnetic equivalent of the polarization of matter we've already discussed. So the key idea here is that matter, i.e. Things made up of atoms, responds to fields. And of course that means both magnetic and electric fields. We saw that for an electric field we could consider the polarization of a material as being proportional to the electric dipole per unit volume. In a material you have two forms of moments, magnetic moments. You have unpaired spins and you have orbital electrons, and these form small magnetic moments which respond to external applied magnetic fields. And so we end up with a material responding to an external magnetic field and giving us what is known as the magnetization. We generally write this as a capital M. It's a vector, and it is, as with the polarization, it is the dipole moment per unit volume. But of course in this case it is the magnetic dipole moment per unit volume, whereas the polarization was the electric dipole moment per unit volume. You will see that there are various parallels between these two cases. We're now going to derive the vector potential for a magnetized piece of material, and some of the manipulations we're going to be doing are very similar to what we did for the polarization, and we'll end up with a final result which will show that we end up with magnetization current densities. And current density, of course, is the source of a magnetic field. Just as with polarization, we ended up with polarization charge densities, and a charge density is the source of an electric field. So let's consider a small volume of material. It's going to have a small volume, let's say dV2, and then it will have a small magnetic dipole moment, delta M. It'll be at a position R2, and delta M will be given by M, the magnetization at the position R2, multiplied by dV2. And then the vector potential due to that small vector, that small magnetic dipole, is given by mu naught over 4 pi delta M crossed with R21 hat divided by R21 squared. So that's the vector potential for a magnetic dipole, which I derived in a previous video. And we're assuming that we can represent the contribution to the vector potential in terms of those dipoles. So now let's integrate over the whole material, and when we do that we can write the following. We'll say that A at the position R1 is going to be given by mu naught over 4 pi, and then we're going to say it's going to be a volume integral. I'll substitute for delta M and write that as capital M crossed with R21 hat divided by R21 squared dV2. And of course really M there should be a function of position, so let's write that in fact as mu naught over 4 pi the volume integral of M at R2, and let's write that in a slightly different form. We're now going to take the cross product with R21 divided by R21 cubed dV2, and you should now look at that and think to yourself, okay, why has he changed it to R21 over R21 cubed? And you should recognize that as the gradient of 1 over R21. So let's just write that down. So we've got mu naught over 4 pi, we have the volume integral of M at R2 crossed with the gradient of 1 over R21 dV2. And the fact that this term R21 vector over R21 cubed can be replaced with the gradient of 1 over R21 is a standard result, which I've already discussed in a previous video. Now this should start to look very familiar, because this is what we did with the polarization charge densities. As we didn't have a cross product, we had a dot product, but again we used the gradient, and then we used a result from vector calculus, and we're going to do the same thing again here. And the result we're going to use this time is that the curl of a scalar multiplied by a vector, I'm writing the scalar as a phi and the vector as an f, is equal to the gradient of phi crossed with f plus phi multiplying the curl of f. Now, we actually have this the other way around in our equation here. So there's going to be a minus sign there. So let's just rearrange that, and we can say that that implies that f crossed with grad phi is equal to phi curl of f minus the curl of phi f. That's a simple bit of manipulation. And we'll substitute that in. We'll see that we've got the vector potential at a point r1 is equal to mu naught over 4 pi into, oh no, let's not do the square bracket there. Let's do an integral, volume integral of the curl of m at r2, and that has to be a curl with respect to r2, otherwise it would be 0, divided by r21 minus the curl of m, again at r2, that's a curl with respect to 2, divided by r21, close the square bracket, so we say it's a dv2. Okay, so now what have we got? This first term looks like something divided by r21, and we have a volume integral. And if you've been paying attention, if you've looked at the previous videos or you've been reading the notes, you'll recognize that generally we say that a is the volume mu naught over 4 pi times the volume integral of a current density divided by a distance. So there's a hint here that this might be something like a current density. It shouldn't surprise you, given that I've been alluding to the fact that this has parallels to the polarization. So we now have this second term that we have to deal with. With the polarization, of course, at this point we had a divergence, and we could do a simple transformation using the divergence theorem. We can actually do a similar transformation here, but it's a slightly less well-known theorem of vector calculus. And the identity is this: the volume integral of the curl of a vector is given by the closed surface integral of the vector crossed with the normal. You can show that if you want to spend a bit of time messing around with vector geometry. So when we substitute that in, we see that we have a at point r1 is equal to mu naught over 4 pi times the volume integral of the curl of m at r2, and that's the curl with respect to 2, divided by r21 dv, minus the closed surface integral of, actually I need to put the prefactor there, mu naught over 4 pi closed surface integral of n crossed with m at r2 divided by r21 dA2, so that's over the surface. And we can, of course, flip those to the n and the m around and change it to a plus sign. And so we finally end up with the formula mu naught over 4 pi. We have a volume integral of something, curl of m at r2 over r21 dv2, there should be a 2 there, plus mu naught over 4 pi times the closed surface integral of something, m crossed with n, divided by r21 dA2. And as I've been alluding to, this something is going to be a volume current density, and this thing here is going to be a surface current density. They're both related to the magnetization. And this again looks very, very similar to what we saw with polarization, but of course because it's magnetization it's a bit more complex, and we're using curls and cross products instead of divergences and dot products. So let's define those densities. We have Jm, the magnetization volume current density, is just the curl of the magnetization, and little jm, which is the surface current density due to magnetization, is m crossed with n. As always, my normal vectors are unit vectors. So that's shown that the vector potential of a magnetized material, if we assume that the magnetized material is simply represented in terms of a dipole density, you can then derive a vector potential in terms of current densities. So now we have to make a slight change. So let's come back to Ampere's law and remind ourselves that we normally have curl B is equal to mu naught J, the current density. But of course that current density is now going to be made up of two parts. It's going to be made up of a free current density and a magnetization current density. And when we were talking about polarization, I noted that I wanted to call the charge density that was from the outside of the material, I wanted to call that the external charge density, not the free charge density as many people refer to it, because I think that free in that sense is confusing. Here, of course, the free current density, free is exactly the right word, because this is a current that is flowing, so we expect that to be free. Let's substitute in for capital JM, and we've got a mu naught into J, the free current density, plus the curl of the magnetization. And you may be able to see where we're going. We've now got a curl on the left-hand side, a curl on the right-hand side, and with a little bit of rearrangement, we can write everything in terms of this free current density. And we're going to define a new field, just as we did for polarization. So when we do that, let's divide by mu naught. So we find that we have the curl of 1 over mu naught times B minus M is equal to J free. And so if we define a new field, which is variously known as the magnetic intensity, or sometimes just H, that is defined as 1 over mu naught B minus M. And it's the magnetic equivalent of the electric displacement, the D field. It is the magnetic field which is produced by a free current density. So in terms of experiments, if we have a coil of wire and we're putting a current through that coil of wire, that is the free current density. That's what we're imposing from the outside. The magnetization current densities that would be induced are magnetization current densities. So H is going to be similarly useful to D. So we have curl of H is equal to J free. If you have a linear material, a linear magnetic material, you can write that M is, let me just rewrite that M because that looks a little bit like an H. M is equal to chi M, the magnetic susceptibility, multiplied by H, at which point we would have that B was equal to mu naught into 1 plus chi M H, which of course you could write as mu naught mu R H in exactly the same way as we did for D and E. In magnetic materials, chi can be both positive and negative, so you have to be just a little bit careful. Most materials have a very, very small chi. Certain materials, for instance iron, known as ferromagnetic materials, have a very large response and they are highly, highly nonlinear. So that's an introduction to the idea that materials respond to magnetic fields. The response to the magnetic field is an induced current density, a magnetization current density, and we can introduce a new field, the magnetic intensity, which we write as the letter H, which only depends on external density, current densities, not on these magnetization current densities, and we will use that to solve in the same way that we use D to solve for the response of electrical materials, dielectric materials to electric fields.